Hello, I'm Sakir Naka, part of Group 19, and this is our video for our final project where we had to design a 32-bit Risc-V processor. And so if you look here, this is our data path, which has the top level I/O being a clock, reset, and this goes into directly the control unit, or the control unit FSM. And this control unit has a bunch of control signals that will output to the rest of the processor. And this is how the FSM will control what the processor does at every state. And the components of the processor are the program counter, the ALU, instruction memory, register file, data memory, and a simple multiplexer that will determine what gets written back to the register file. And here is just a picture of the RTL schematic that we get from Vivado when we run it, and this is just the same as this data path. Now if we scroll down here, this is our FSM, and so we start out in SPC0, which is the initial state, and this is where we read the value from the PC, and then we step through, and for every single instruction we're going to go through to imread, regfile, dmem, regfile, PC, and then back to the initial state, with the exception of instruction ecall and ebreak, which will go here. Oops. With the exception of ecall and ebreak, which will then halt the program. And even if the instruction does not say use data memory at all, it will still step into the data memory state, except for that instruction, all the control signals that we talked about earlier, which are these right here, imread, regread, etc., it will just be 0, meaning that nothing happens at that state. For this reason, every single instruction, except for ecall and ebreak, will take exactly 5 cycles, because that's just the way that our finite state machine has been structured, and which in addition is a annealing machine. And here's another description of what each state is. So we start out in PC0, where we read the value of the PC. Then we go to imread, where we read the instruction. Then we go to regfile, where we read the values from the register and reload those. And then dmem, where we access data memory and either read or write depending on the instruction. And then regfile is where we read back, or rather write back if we need to do so. And PC5 is when we update the program counter with the new program for a new program counter for the value for the next instruction, and then we just loop back to the start of our FSM. Now, basically, the way we've tested our processor is by having a number of instructions in a memory file, and then we will run these instructions, and then we will inspect the values of the component of the processor. So for add, we're going to run some add statements, and then we will read the reg file, and then we will compare that with our manually done reg file, and we should be able to compare and see that the instructions work properly. So for example, here's a simulation, and so we do these instructions, and then it runs them, and it will update the reg file. As you can see, R3 is updated with the value 1, and then the same with here. So if I run this, the way we set this up is we go into the test bench, or sorry, not test bench, we go into the instruction memory, and we make sure that the the instruction we want to test is uncommented. Sorry, pardon me. Just taking a second, sorry. Okay. So now we want add I, which is going to read this mem file, and it's going to run these 4 commands. And so we will run the simulation, and basically it will go through and it will run these commands and generate a reg file out to the processor, or rather to the test bench. And we need to also make sure that in the test bench that this line is properly set, and then we run the simulation. You see, we didn't have it properly set before, and it gave an error because it didn't match the proper results. But now when we run it, the reg file out that sends back to the test bench will be checked against our written one, and it should give the right answer. So now we can see that now it's properly set up, all tests are passed successfully, and the reg file out has been checked against our manually done reg file, and which is this. And so we'll check against this and make sure all the values are correct. And then moving on, here are some high-level test cases. What we did were Booth's algorithm for sign multiplication, and factorial, where we basically did 9 factorial plus 8 factorial and 9 factorial minus 8 factorial. And then we inspected the outputs, the reg file and the data memory, and we found that the program properly gave the correct answers. So here, if we run, for example, let's say we run the factorial one. So the way we do this is we would have to set this as a top file, and then here we want it to run instructions.mem. We'll save, we'll run the simulation, force the clock, run the initial reset, set that back down to 0, and now we'll run our code until the program has finished executing. As you can see, and this is our program's execution of it going through all the different instructions. As you can see here, these are the different instructions that it's running. And if we look at the reg file, 16 and 17 are supposed to hold the values for the factorial expressions, and as you can see, these values are correct. And so that's how we've done our test cases, our complex test cases. And for ways that we can improve our design, one way that we can improve our design is that we have a fixed set of instructions that we've implemented. However, if there is a common grouping of instructions that are done a lot, we could instead create one instruction that does that whole thing, which would make the processor a little bit more complex, but it would reduce runtime overall by having less clock cycles if this is a instruction that is used often. And then another way to improve the performance of our processor would be to change our finite state machine a little bit, because right now every single instruction will take 5 clock cycles, but not all these instructions necessarily need to take 5 clock cycles. So if we made a more complicated FSM that can skip intermediate states, depending on what kind of instruction we are currently running, we can require less clock cycles in order to run a program and therefore improve and optimize our processor. And so yeah, that's basically our 32-bit Risc-V processor. So yeah.